All right, so let's go over the roots of unity, what they are, some examples of what we know, and then how to find certain roots of unity. So the first step is the definition. A root of unity is a number x such that we can raise it to some power n, could be 1, 2, 3, etc. But the point is that when we raise x to that power n, we get 1 back. Or in other words, it just satisfies the equation at the bottom, x to the n equals 1. Now, as for some examples of numbers that we already know, -1 is a root of unity since -1 squared, or -1 to the second power, gives us 1. In other words, there does exist some power of -1 that gives us 1 back. However, note that -1 to the fourth, -1 to the sixth, and pretty much any even power gives us 1, but we only really care that some power of -1 gives us 1, so at least 1. On the other hand, also notice that 1 is the root of unity since it's kind of trivial, but 1 to any power n gives us 1. So 1 to 1, 1 squared, 1 cubed, and so on. The idea of finding some specific roots of unity is just to kind of play around with the equations and then try to make use of the zero product property by either factoring or using the quadratic formula. So let's look at specifics like the second root of unity. What that is just a root of unity, specifically when n equals 2. So we have the equation x squared equals 1. Now, we could guess and check to see what x's actually work, but to make sure that we have all of them, let's play around with the equation a little bit and just bring the 1 over to the left-hand side, so we get x squared minus 1 equals 0. Now, notice we have a quadratic at this point, so we have two options. We can either use the quadratic formula, which will give us an x, or basically all our solutions, or we can factor this using our identity that a squared minus b squared equals quantity a plus b times quantity a minus b. So using that, we get that x plus 1 times x minus 1 equals 0, and then kind of like applying the zero product property, we just have to find out when x plus 1 is 0 and x minus 1 is 0. Either case, we get that x has to be plus or minus 1. And those are our only solutions. Another case is the third root of unity, which is when n equals 3. Now for this, we have the equation x cubed equals 1, or again, x cubed minus 1 equals 0. Now for this one, we're actually going to use the identity a cubed minus b cubed equals a minus b times a squared plus ab plus b squared. So we can factor this into x minus 1 times x squared plus x plus 1 equals 0. Again, we can make use of the zero product property to find out when each factor is equal to 0. Now the first factor is easy. We can just see that x equals 1, and that's a real solution. But for the second factor, we're going to have to use the quadratic formula. And you'll notice we'll actually get a complex number. So depending if we want all solutions including complex, all of these answers, 1 and those complex numbers, are legitimate solutions. But if we're only talking about real solutions, we only have 1. Now for our last case, the fourth root of unity is again when n equals 4, and we have the equations x to the fourth equals 1, or again x to the fourth minus 1 equals 0. Now for this one, it's actually like the second root of unity, where we use this identity a squared minus b squared, and we can get that x to the fourth minus 1 is actually x squared minus 1 times x squared plus 1, which gives us 0. That's what we want. So we actually know the solutions to x squared minus 1, which we did in the second root of unity, and that's just plus or minus 1. But for the second factor, x squared plus 1, we're going to have to use the quadratic formula because we can't actually factor. And again, you'll notice that we actually get complex numbers. So again, it just depends if we're talking about reals or including complex, but all of these are legitimate answers to this equation, or the roots of unity. And that's how we find these specific roots of unity, by trying to make use of the zero product property and factoring or using the quadratic formula that we know so far, and then seeing if we get real solutions or complex solutions and being able to distinguish what we want, real or complex, or both.